Okay, so in this example, I'm going to be solving a beam kind of problem using a sine series, Fourier sine series. So this kind of question is helpful for the exam and the assignments that we learned in class. So I'm going to first start off with our question, and question is going to look something like this. We have a simply supported beam here with a load coming down. Right? Say it's simply supported. And we know that this side is starting at 0, this side is going to L. So we know that the whole span here is L. And we're also given that the loading that is represented on this beam is Wx equals W naught x over EI L, because we're going along the entire span. So for this kind of question, your first step is to figure out your period of your function and then substitute everything into your equations. So the best thing to do is start off by figuring out what your period is going to be. So if I have something that looks like this, and then something that looks like this, and then something that looks like this, and something that looks like this, I want to figure out, going from negative to the positive, what is this? And in this case, it's 2L. So I'm going from the negative part of this to the positive part of this. So L and then another L equals 2L. And we learned that T equals 2P. T is your fundamental period, which in our case is 2L, and P is your period. So we have 2L equals 2P, and then L equals P. So that's our function. So another thing is for our beam functions. For beams, we take them as odd functions. So when we take a function as an odd function, we can use a Fourier sine series to solve our beam. So since we have a odd function, we can also say that a naught and an are equal to 0. I'm not going to do the proof for these, but you can find that these two will equal 0 if you try to solve for them, in this case. This is an odd function. But we will have a Bn. We don't know what it is, but we're going to have to solve for it. So our next step is to represent the loading on this beam using a function. We can say that our loading, Wx, is equal to summation from infinity n equals 1 Bn times sine n pi x over p. So what we're going to do, we're going to be solving for Bn, and then we're going to be looking for our load function, and then solving for the particular solution, verifying that our boundary conditions are met. So our function right here for B of n is going to look something like this. B of n is equal to 2 over p, in this case for our odd series, integrating from p to 0, f of x times sine n pi x over p dx. Alright, so this is our first step to set up our equation to solve for our coefficients. Okay, so now we can start substituting stuff in that we know. Our load function in this case is going to be this. And, oh no, sorry, our load function is going to be this right here. And our P is going to be L, which we derived right here. So we can start plugging things in for B of n. So Bn is going to be equal to 2L, 2 over L, from L to 0. Our function, in this case, W naught times x over EIL times sine n pi x over L dx. So in this case, this looks like a something that we can integrate from 0 to L. But the first thing that I will do is I will pull out our constants. Pulling out the constants makes it easier for me to do integration. So if I pull out the constants, I'll get 2 over here. I'll get W naught. Oh, can't pull out the x. Can only pull out constants. Divided by EI. L times L is L squared. Still have L here, still have 0. Inside I have x times sine n pi x over L dx. So you'll notice that this part of my function is something that's called, is something that we can solve using integration by parts. So you can do this part using integration by parts and then plugging in your limits from 0 to L. But to save time, you can just look on your formula sheet that's provided and you'll get a simplification for this integral. So if you look on your formula sheet, the simplification for this integral is -1 n plus 1 times p squared over n pi, right? But remember, our p is L, so we can rewrite this as -1 n plus 1 times L squared n pi. Okay? So now, what we can do, we can rewrite our Bn. Bn equals 2W naught over EI L squared, and this gets simplified to this. So I get -1 n plus 1 over n pi. Okay? So this is what our Bn equals. So we can plug this back into our function right here because we've solved for Bn. So our Wx function, or our load function, is going to be equal to the summation from infinity n equals 1 of Bn, which we just solved, 2W naught over EI. Oh, we forgot our L squared. I forgot my L squared here. There's L squared here. These two will cancel. So we got EI. Over here we got -1 n plus 1 n pi over here. And this is going to be multiplied by sine n pi x over L. Okay? So this is my Wx function that I solved for. So the next step, we're going to have to verify that all our boundary conditions are satisfied, meaning each boundary condition has to equal its subsequent value. For example, deflection has to be equal to 0 at this end, so y of 0 equals 0, moment at 0 equals 0, deflection at L equals 0, and moment at L equals 0, you have to verify that these are all satisfied before you proceed to solving your particular solution. So make sure these are satisfied. I'm not going to go over it right now in this video, but usually they do work out, and you're just going to have to make sure that those are met. Once you find that your boundary conditions are met, so you have to say your boundary conditions are met, so you can give it a check mark. Then you can proceed to solving your particular solution. So your particular solution is going to be very similar to what we solved before, but now you're equating coefficients using both sides of your equation. So in this case, I'm going to assume a particular solution of yp equals the summation of infinity n equals 1 bn times sine n pi x over L. So this is a particular solution we can assume. So always assume a particular solution that you think makes sense for your problem. In this case, we're using a sine series problem. We're choosing something that looks similar to our function. So on the exam, you're going to have to memorize a few particular solutions that you can use. And I'm going to go with this format for this question. So once you get to this step, you're going to want to take the derivative of this function 4 times because we want to get the load function. Remember, loading is represented as the fourth order differential equation. And if we don't have our fourth order differential equation, we can't equate coefficients in our other formula. So let's start off by taking the derivatives. So the first derivative, again, summation from infinity to n equals 1. I still have bn here. The derivative of sine is cosine, but since I have this stuff inside here, I have to do the chain rule. So I get n pi over L cosine n pi x over L. Alright, take the derivative again. Yp double prime equals summation infinity n equals 1 bn. The derivative of cosine is negative sign, so bring out the negative symbol. N squared pi squared L squared sine n pi x over L. Third derivative, infinity n equals 1 bn. The derivative of sine is cosine, so negative n cubed pi cubed L cubed cosine n pi x over L. Fourth derivative is equal to infinity n equals 1 bn. Derivative of cosine is negative sign, so negative times negative is positive. N to the 4 pi to the 4 L to the 4 sine n pi x over L. Okay, so you have this, and once you get to this step, you can equate what we got in our previous solution to what we are now going to use for on both sides. So in the previous solution, we found that our wx function equals this, and we can equate both sides. So what we're going to do, we're going to set summation. Basically, we're going to take this, make it equal to this, and solve for bn, and then we'll be done. So n equals 1, 2 w naught over ei, negative 1, n plus 1, over n pi times sine n pi x over L equals summation infinity n equals 1 bn n to the 4 pi to the 4 L to the 4 sine n pi x over L. Okay, so now I'm going to equate both coefficients. I can disregard the signs, take these two and find Bn. So I get 2W naught over EI, negative 1 n plus 1 n pi equals Bn, n to the 4, pi to the 4, L to the 4. And now I'm going to solve for Bn. So if you equate both sides, you're going to get a final solution of Bn equals 2W naught L to the 4 negative 1 n plus 1 divided by n to the 5th power pi to the 5th power EI, right? And that's going to be your Bn. So after you got Bn, you're simply going to substitute it back into your particular solution right here, and that will be your final solution. So yp is going to be equal to the summation infinity n equals 1 Bn, which is 2W naught L to the 4 negative 1 n plus 1 over n to the 5 pi to the 5 EI. We're going to multiply it by sine n pi x over L. Sine n pi x over L. Alright? So that's what we have for our final solution. So you can see that we can use a Fourier sine series to solve a beam problem. And I'll be solving more questions later on.